Okay. Yes. All right. Okay. Well, happy Monday, and this is our last lecture for 102B. It's a little sad for me, I guess, but I feel okay. All right, and you guys have your final exam on Wednesday. And I listed out all the topics that you need to know for the final, and I've pretty much written the final, and I've tried to stick to the list of topics as I've put them on CCLE. I think it's fair. Of course, I feel that way, but I try to. The intent is to be fair, okay? And I hope the questions that you see on the midterm reflect that. I don't know. Are there any questions before I get started? Talking about PCA? Yeah. Okay.
When we got homework grades back, and for homework 3, you had like that 24-hour extension.
Yeah.
Like it still kind of like further late.
Oh, okay. I better tell our grader. Something. Must have been a misunderstanding or something. Okay, I'll go back and I'll fix all that. Okay. All right. Yeah. Okay. Sorry about that. We'll make sure. So, yeah. Okay. I'll go back and we'll make sure your homeworks are graded correctly. So homework. So I think up through homework 3 has been graded. Okay. Because homework 4. Well, I know. And then the homework 5 is due on Friday, right? Okay. And or no, wait, maybe homework 3 has not yet been graded. But okay. But okay, oh yeah. So that's fine. Okay. The due date, the deadline didn't change. We just extended the grace period. Okay. So on CCLE, it will say, as long as it says less than 1 day late, you won't receive a penalty. Okay. All right. Is that all right?
Because it says 3 hours late. And it's like...
Yeah. It is technically 3 hours late, but there's no penalty for anything less than 24 hours late. Okay. All right. So, yeah, the homeworks will get graded, and yeah, just please be patient with that. Okay. Topics for the final. I looked at this when I wrote it. Okay. Of course. The examples will not be exactly the same, but it's pretty much the same. Yeah. Question?
Yeah, also about problem 5, you're just right there. So this k-means with kernel transforms. So will we transform without transform?
So you have k-means without transforms in problem 4. Okay. Yeah. So you'll do some clustering without transformations for problem 4, and then for problem 5. There'll be transformations. This is not, you aren't doing the kernel distance. You know, that crazy thing with the double, you know, the sum and the double sum. That's how we calculate the kernelized distance, but you will not do that. Okay. All right. Okay. All right. So I hesitate to say this. All right. So today we're going to cover PCA, Principal Components Analysis. I think it's a really interesting topic. It's a pretty important topic, okay? But I will not put PCA questions on the final, with the exception of like one question or a couple questions in the conceptual part, okay? So only in a conceptual question there might be a few questions, couple questions on PCA, but other than that, I won't have you do like PCA calculations or derivations or anything like that, okay? Please don't just mentally check out of today's lecture, though, okay? I know how it is, where as soon as someone says it's not going to be tested on the final, you're just like, I don't need to pay attention at all, right? But it's but we need it, okay? So so what is principal components analysis? Okay, it is most frequently used for dimension reduction, okay? Dimension reduction. And it falls under unsupervised learning, okay? Because there's no answers to try to match up with, right? So with supervised learning, there's always some kind of answers that you're trying to line up with. There's always some kind of target, and you try to get close to that, and you measure how far you off from your target as a way to figure out how much you can improve. And with PCA, we don't have that. With PCA, we are just looking for structure in the data, and specifically the structure that we're looking for is we kind of want to reduce the number of dimensions. So we might have so like in, I don't know, 101A or 101C, I don't know, did you ever have to do with like a housing data set, housing prices and stuff? Okay, this is a common thing that we like to do in our stats classes because it illustrates a lot of stuff here, right? And if you look at housing, like overall, what kind of things affect the cost of a house? The size of the house, the square footage, the area of the house. Okay, what else? Oh, and the location, the area location in terms of like, is the house in Beverly Hills or is it in Van Nuys or is it in I don't know, some other part of the city? Okay, is it near, you know, is it near next to UCLA? It's going to be expensive. Is it if it's, you know, somewhere, you know, there's different spots in the right? Is it along the beach? It's going to cost more, things like that. Yeah. Okay. Anything else affect house price?
Number of beds and baths.
Yeah, number of beds, number of baths, and stuff like that, right? Okay. So probably in your data set, there's like, I don't know, 60 variables or something, right? And it lists off all of these things, right? It's like number of beds, number of baths, square footage of the lot, square footage of the basement, and maybe you have information about the neighborhood that it's in, and it might be like median price of the surrounding 5 houses, like the 5 nearest houses, you know, the school ratings in that neighborhood, the crime rate in that neighborhood. There might be other things like what kind of, like the quality of the kitchen, the quality of the floors, the quality of the roof, how recently it was remodeled. Like, I don't know, is there a garage or stuff like that, right? Okay, and you can do an analysis, and there might be a ton, like you got all these variables, and what's a problem that you have when you have a whole bunch of variables and a lot of them are correlated? So, for example, if we're looking at housing prices and stuff, you're going to see high correlation between the number of bedrooms and the number of bathrooms and the square footage of the house, right? In general, as you have more bedrooms, you're going to have more square footage and more bathrooms, right? So there's going to be high correlation with a lot of these numbers. So what's an issue that you have when you have high correlation between your predictors? Yeah. Overfitting, okay. And more specifically, what happens? High VIF, yeah. So you have, basically you have high variance in the coefficients, okay? So one person can have a data set, okay, and they have, let's say they have all the same variables and they got, you know, a bunch of observations, and it might turn out in that thing that the square footage is the most important thing, and square footage has a high, like a fairly large coefficient associated with it, okay? However, someone else can take basically another set of data, same predictors, but just because of the random nature of the sample, in their sample, it might turn out that the number of bedrooms is the most important predictor, or something like that, okay? And so you might get like seemingly results that seem to disagree with each other, you know? So what is it? Is it more square footage that's more important? Is it the number of bedrooms that's more important, right? And maybe depending on who you talk to, they might say different things, right? And similarly, you know, one data set might say, oh, you know what, it's the school ratings that are important. And another data set will say, you know what, it's the crime rate of the neighborhood that's important, or something like that, okay? And there might be disagreement about which of these things are important, okay? But if we take a step back, those aren't necessarily in disagreement, okay? If we instead, rather than saying, let's figure out whether it's the number of bedrooms or the number of square footage, what if we just kind of grouped these variables together and said, we've got some attribute that describes the size of the house, okay? And the size of the house is important. Bigger houses cost more, smaller houses cost less. And there's different ways to measure the size of the house. Sometimes we use square foot, sometimes we use bedroom, sometimes, you know, some other aspect, okay? It's the size that's important. And which exact variable, maybe another, okay? And then maybe another variable is the neighborhood is an important factor in the cost of the house. And whether that neighborhood is measured using crime rate or school quality or whatever, how many parks are in the vicinity or something like that, you know, what shopping center is nearby, right? So if there's, I think somebody did a thing where they said neighborhoods where there's a Whole Foods versus neighborhoods where there's a Walmart, okay? And if there's a Whole Foods, it means the houses are expensive. And if there's a Walmart, the houses cost less, okay? I mean, that's general findings, okay? Yeah?
So, like, let's say there's two variables that are correlated, like neighborhood, let's say, like, a neighborhood with Whole Foods and, like, you know, like houses with 2 rooms. If those are correlated for whatever reason, is that, like, a limitation of the model? They wouldn't be in the same category, but they're still correlated.
Yeah, so I think we're getting to kind of maybe the results of the PCA, what you're talking about. And so basically, you can take our housing data set, which might have like 60 variables with, you know, number of bedrooms, number of bathrooms, square footage and stuff, and maybe we can reduce it to just like 3 overarching variables, okay? 1, size of the house. 2, how nice the neighborhood is. And 3, like the amenities and like furnishings within the house. Like, are the walls nice or are they falling apart, you know? Is it a fixer-upper or is it like move-in ready type of thing, okay? And maybe those are really just kind of the 3 overarching things that might manifest slightly differently with these individual variables. And so, you know, you might find a thing where the 2 things are correlated or not correlated or things like that. But that's what PCA will be able to discover, okay? And the thing about PCA is it doesn't, so here we kind of talked about it, okay? And reasoned through and said, like, it makes sense for these variables to be grouped together. PCA doesn't know, okay? PCA is just this thing that we do with the numbers, but it says, hey, look at this. You showed me a whole bunch of numeric variables, and I'm able to basically preserve the variation that we see in the data, even though I'm keeping only a subset, okay? Or even though I'm not even keeping, but like creating just a few actual variables. Okay, so I think this is kind of the example I've talked through. So in housing prices, we've got all of these things. And maybe we can reduce them. Can we reduce from all of these variables to just something like this, right? So the size, which might consist of these variables, the amenities and the quality, which might consist of these things, and the neighborhood desirability. And that's basically the goal of PCA, is to discover something like this. Now, this is something we did, I don't know, semantically, talking about the variables. But again, PCA, it doesn't actually reason through this. It just says, here's the numeric variables that we've seen, and I am still able to kind of preserve the nature of the variation in the data despite only using only a few variables, okay? And so what PCA will do is it creates new numeric variables that are just linear combinations of other variables, okay? So linear combination just means you multiply the value by a constant, and then you add it to like another variable, okay? So nonlinear would be like you can square it, or you take the square root, or you take the exponent or something. But here we're just multiplying it by a constant, okay? And that's what makes it a linear thing. Here's some other examples of dimension reduction, okay? And dimension reduction is a very useful thing because our brains have a hard time thinking about a bunch of variables all at once, okay? We can probably handle maybe 5 variables or 6 variables at once, but once it gets beyond that, it's really hard for our brains to handle, right? So trying to keep track of the housing data set where we've got like 60 variables or something like that, it's too hard. So it's much easier to just reduce it down to kind of three variables, okay? And so, you know, kind of in that vein, GPA reduces your entire academic performance to one number, and it makes it easy to compare students to each other using just this one number. You know, which obviously has its pros and cons, right? When you reduce something down to one variable, you lose information, okay? Maybe you preserve something. You preserve like students with higher grades versus students with lower grades, but you lose a lot of other information, right? There might be a good reason why the GPAs are different, right? Did the student major in hard class, I mean, take a bunch of hard classes or easy classes, right? Did they, you know, there's often a comparison between North and South Campus majors and the GPA difference, and it's a real effect. It's a real thing that exists. And that's not if you only look at the GPA, right? Like, if on your resume you didn't put your major, but you just had GPA, if like that was a thing, okay, nobody would choose a hard major, right? But people are saying like, okay, well, if I've got statistics, this GPA, that's going to look better than I don't know what the stereotypical super easy major is, right? But yeah, underwater basket weaving is the joke major or something, right? Home economics or something. I don't think is offered anymore. I know people who truly were home economics majors when they went to college. They're like 70 years old, but when they went to college, you know, she was a home ec major. Okay. So anyway, that's what it is and stuff like that. So okay, SAT GRE. Basically, there's something very complex, right? Like, what is your, I don't even know if this is what it's trying to measure, your intellectual aptitude or something, and it reduces it down to like 2 numbers, maybe 3 numbers, right? Like, this is how good you are at words and numbers and writing, okay? You know, intelligence is a lot more complex than that, but maybe it's useful, okay? Credit scores, I don't know, do you guys have to worry about your credit score yet and stuff? And anyway, people are saying maybe the credit score is not even a good thing now, but it's like, you know, if I lend you money, can I expect you to pay me back? And there's this number that says, yes, this person will pay me back. Or, I don't know, the person might not pay you back, right? They might take your money and just say, oh, sorry, I can't pay you back. And that happens, right? And so, you know, we take all of your financial transactions and then say, boom, your number is 700 or 800 or 600 or 300 or something, okay? If you're a football player or if you're into the NFL, you get like, the quarterback gets a passer rating, and it's this complicated thing, but it's basically if the quarterback threw the ball and it didn't get intercepted, had a good performance, You get a high passer rating if the quarterback sucks, throws interceptions, gets tackled and sacked and things like that. Bad passer rating, okay? And stuff like that, okay? Or, you know, in the Olympics, track and field, there's like the heptathlon where they like jump and run and hurdles and javelin or something like that. Obviously, you've got different events, but we need to have a way to rank them to gold, silver, bronze, right? We need a way to rank them. And so that event has its own way of dimension reduction to take the results of these individual events, 7 different things, and shrink them down to one score, right? So, you know, yeah.
I thought dimension reduction would just be getting rid of irrelevant dimensions.
Well, it's not just getting rid of irrelevant, because how do we deem what is an irrelevant dimension?
I don't know, statistical power.
Yeah. So this is, PCA is a way to kind of take a look at the entire data set and determine which of these variables play an important role in variation, right? And so that's what we do. Okay, so the math stuff, I think, did I put it on the next? The next thing. Okay, so here is maybe just a little bit of an illustration. Okay. So one idea of dimension reduction is this idea of projection, okay? And so, you know, this is what we do constantly, all right? Okay, so here, my hand is casting a shadow onto the screen, okay? So my hand exists in 3D, okay? But when the shadow it casts on the screen is in 2D, okay? And so there are different ways I can position my hand, okay, and it will cast different shadows, right? So if I position it like this, the shadow that it casts doesn't quite look like a hand, okay? I mean, whatever, you know, okay? But if I position it this way, it's very clear that it's a hand, okay? And so there's different ways we can project something, right? All right, this is an uninteresting object, but here, you know, here we have a book, okay, and it casts a shadow that like that looks like a book, right? Okay, and if I do it this way, it's less clear. It's less clear what this is. Okay, this could be like a remote control or something, right? And so you know, whatever the object is, we can think of like, so here's a battery, and if I do it like this and you see the little tip of the battery, then you're like, oh, that's probably a battery, right? But if I hold it this way, okay, then it's very difficult to tell what object it is, right? So what we want to do is we want to reduce from a higher dimensional thing like 3D down to 2D. This is reducing down to just 1 dimension, but similarly, you know, 50 dimensions down to like 2 dimensions or 3 dimensions. But we want to do it in such a way that the structure of the object, the original data set, is preserved and not done in such a way where we can't really tell what we're looking at. Okay, Yoni, did you have a question?
So last time we learned how to project lower dimensions, we learned about something that projects lower dimensions to higher dimensions.
Yes.
And now we're basically learning the opposite.
Right. So with kernel functions, we take lower dimensional data and we project it into higher dimensions, and we do that so that we can find a linear boundary to separate things, okay? And yeah, with PCA, we're doing kind of the opposite, where we have this high dimensional data set, and we say, oh, the high dimensions, this is too hard for our brain to wrap around. Can we project it down to a simple, like, to fewer dimensions, okay? And so here we've got this going from 3D to 2D stuff, but we can go from 70 dimensions down to 5 dimensions or something like that, okay? And it's easier to kind of keep track of 5 dimensions than it is to keep track of, you know, 100, right? If you've ever played like a role-playing game or something like that, you have like this character sheet, right? And you've got different attributes, right? Like strength and intelligence and perception and I don't know, whatever else you have, right? Depending, like agility and stuff. And you're basically reducing a complex thing such as a human or a orc or whatever down to just a few numbers, okay? And you know, you can do that with actual humans too, but probably you shouldn't, right? It's good to leave things in their complex form here. So anyway, so this is just kind of maybe an idea of this idea of projection, okay? So how does projection work, okay? Well, the way we're going to do the projection, okay, is we're going to take our original data, which exists in n dimensions, okay? I'm sorry, not n dimensions. In d dimensions, our original data. Okay, sorry, I've got this all messed up here. Okay, the original data is in m dimensions, okay, and we have n observations in m dimensions. This is the original data, okay. And what we do, okay, is we are going to multiply this by a vector. Take the nth observation, which is in m dimensions. We're going to multiply it by a vector called w, okay? W is a 1 by m vector, okay? So when we do 1 by m times the nth observation in y, this is going to create a single value, okay? So this WD transpose times yn will create a single scalar value, yeah.
So y is variable y, or is it like x, y, z?
So y is kind of our original data set. Maybe this is in 60 dimensions, okay? So maybe you have 100 observations in 60 dimensions, okay? So y would be, all of y would be 100 by 60, okay? And here we're just going to say, let's take the first observation, okay? The first observation, y sub at 1, okay, is going to be just a vector of 60 values, okay? This is the first observation. It's 60 dimensions, okay? So we have this, okay? And what we're going to do is we are going to make a linear combination by just multiplying y times this vector w, kind of our weights, okay? And so we have 60 weights here, and when we multiply those 60 weights times this, and we do this matrix multiplication, it's going to take all of the values in y, all 60 of them, multiply each of them by a different weight, and add them together. Okay, and that's going to produce one value here. Okay, and so this x sub nd, okay, this is going to be x1, and maybe we'll just do it the first one, x11. This is going to be a single value. Now, let's say we want to reduce our 60 dimensions down to, say, 3 dimensions. Okay, if we want to reduce from 60 dimensions down to 3 dimensions, we are going to have 3 different w sub d's. We're going to have a w1 for the first dimension that we've reduced to, a w2 for the second dimension, and then w3 for the third dimension. Yeah. Yeah.
So are there 100 y vectors if there's 100 observations?
Yes, there's 100 y vectors. Each of those y vectors have 60 values in them. Okay, and then if I'm reducing from 60 dimensions down to 3 dimensions, I'm going to have 3 weight vectors, 3 w vectors. Okay, and each of those w vectors will have 60 weights in them. All right. All right, so here's an overly simplistic idea that it doesn't work this way in real life, but it could. I mean, theoretically it could. Okay, so imagine our housing data set, okay, where we had 60 variables in it, okay, and we said one variable is the size of the house, one variable is the neighborhood desirability, and one is like the amenities of the house, okay? And And the most simple example is maybe our W's just have a whole bunch of ones and zeros, okay? And so maybe for the size, we're going to get a 1 for the variable square footage and a 1 for the variable bedroom size, number of bedrooms, and a 1 for number of bathrooms, and 1 for lot size. And then we're going to get 0 for things like crime rate, 0 for school ratings, 0 for quality of the kitchen, and 0 for, 0 for all of the other things, okay? And that might be the first thing. And so if I multiply that times the vector y, we're going to get, basically, we've taken all the variables related to housing size, and I've multiplied them by 1, and I've added them together, and everything else just gets a 0 and gets thrown away. Okay? And then maybe the second variable, which is neighborhood desirability, we'll have a 0 for square footage, a 0 for bedrooms, and a 0 for bathrooms, but then a 1 for school rating, and a 1 for crime rate, and a 1 for, I don't know, whatever, number of parks and things like that. And then when I multiply that weight by y sub n, then we get a linear combination of these things, which basically just says, let's add up these neighborhood ratings together and throw everything else away, okay? And then, we might have that for the quality of the house. Does that kind of make sense, what we're doing? Yeah.
So each W vector would have the 60 columns.
Yeah.
And then when you say add them up, you're talking about just producing that one scalar.
Right.
Okay.
Yeah. So each W is going to have 60 values in it because your original data has 60 variables. So you need to have kind of the recipe for, here's our 60 variables. What's the recipe that we use to combine? Okay. And maybe, depending on how it's measured, you might even have a negative thing there, right? So if we want neighborhood quality, okay, we want high school ratings but low crime rate. So maybe crime rate might get a negative value associated with it, so that when we add them together, overall higher values mean good things and lower values mean bad things. Yeah.
Is the weight what allows us to transform it in a way that looks like good?
Yeah. So the weight, yeah, we're doing a linear combination, okay? We're basically adding these 60 variables together in our original data set, but we're giving them different weights, okay? We're saying, I want...
Is that what makes the process that allows us to do the projection that looks good?
Yes, yeah. So we want to find the correct combination that's going to give us the best projection, yeah.
So how come? I guess you might get to it at some point.
So how come? Or how do we do it?
Something like that.
Yeah. So yeah, I'll get there, okay? But this is conceptually what we're doing, okay? We're multiplying each of these variables. There's 60 values in y, and we're going to multiply them by some value, okay? All 60 of them gets multiplied by a different value, and then we add them together, and that produces this. And so when we've reduced y, which exists in 60 dimensions, we're going to get x, which now has 3 values. Okay? And so the notion that we're going for is we want to maximize the variation that we've captured in the resulting projected space. Okay? So with 60 variables, we've got all sorts of different kinds of variation, right? We might find a house that is very small but has really nice kitchens and floors and something. I don't know. You might even have a house, okay, or actually a better example would be you might have a small, tiny house but is divided into 6 bedrooms, okay? Each the size of a closet or something like that, right? It's possible, right? Probably not common, but we might have that, right? And then you might even have a giant house where there's only a couple bedrooms because each of those bedrooms are huge and I don't know, right? So it's possible. And so, but overall, most houses, bigger houses will have more bedrooms, smaller houses will have fewer bedrooms. But, if we want the true variation that exists in our data set, we would need all the variables to say, all right, here's this one house that's weird where it's really tiny but it's got a bunch of bedrooms, and here's this other house that's also weird because it's really huge but it's only got a couple bedrooms in it. Yeah. Okay, another question. Yeah.
Did you say how you got the weight to
I haven't gotten there yet, okay? I'm just talking about conceptually, this is the goal that we're going for. Okay. Yeah, and so so we're going to maximize the variation captured in the resulting projection space. Okay, and to kind of keep things, to avoid us having infinitely many solutions, we are going to say that the resulting projected dimension is orthogonal to all the other projected dimensions. Okay, and this is like getting into your weird linear algebra. Not weird, it's a totally basic aspect of linear algebra, but maybe you've forgotten it. Okay, so to have vectors that are orthogonal means their dot product is 0. Okay, and so what we want is that when I do the weights for the first component, okay, like the weight for housing size versus the weights for neighborhood desirability, I want those to be orthogonal to each other. Okay, basically I don't want any information that's already contained in the house size variable to also be contained in the neighborhood desirability variable. Okay, so I want those to be orthogonal, otherwise what's the point? Yeah.
So Wi is just one of the...
Yeah, one of the weights, okay, and Wj is another vector of weights. And we want... Yeah, so again, if we have 60 variables in our original data set, our weight vector is 60 values long.
But isn't Wi just one of those values?
No, it's one of those weight vectors, okay? So Wi is a vector of 60 weights. So it's...
So we have 100 weight vectors?
No, you have D. So if I'm going from 60 dimensions down to 3 dimensions, okay, I'm going to have 3 weight vectors. Each of those weight vectors have 60 values in it. Yeah?
What's the implication if you can somehow reduce it to just 1? Like, what if D is 1? Like, that's it. Like, you reduce it to just 1.
You can, okay. So, all right, when you say you can, the answer is you can always reduce it down to 1 dimension, but you lose information, right? Like when we've taken, so technically, your academic performance at this school has like a bajillion dimensions to it, okay? Because we've got to take into account which class you took it, when you took it, who was your professor, all of these things, right? And so technically, the university could maintains all of this in your thing, and we have it, but we reduce it down to 1 dimension, right? And so your GPA, okay? And so so when you do that, you lose information, right? Somebody has a 3.6 GPA and somebody has a 3.8 GPA, okay? And right now, if we look just only at those numbers, do we know that the difference in GPA is because this person had a really hard professor for this one class, or this person had majored in or took all of these easy classes, you know, easy A classes or things like that, right? We don't know. So you can always reduce down to 1 dimension, but you might lose information, or maybe you lose some information, but maybe it's not that big of a deal. Okay.
So it's like if we take all like SAT scores and just shove it together into one giant composite score, we kind of lose whether we're better at writing or better.
Exactly. Yeah. So yeah, if you say I got, but you know, if somebody says I got a 1500 on the SAT, you're gonna be like, okay, you did well on the SAT, and we don't really care. Was it because you got 750 math, 750 verbal, or did you get 800 math, 700 verbal, or vice versa? We're just like, oh, 1500. That's good, right? And so yeah, you can take all of these things and reduce it down to 1 composite score. Okay. Do you lose information? Yes, you lose some information. Are you losing a lot of information? Maybe, maybe not. You have to think, how many students are going to get, like if somebody says my total SAT score was 1100, okay, you can probably say, oh, okay, probably something around 550, okay? Could it be a student who got 800, 300, or 300, 800, did math verbal? Could be, but how often is that going to happen? Probably not very often, right? Like 800 math and 300 verbal, or vice versa, 800 verbal, 300 math. There's probably not a lot of students like that, okay? You might have like 600 on one side and 500 on the other, or maybe even 650 and 450, like, but once you start going beyond that, like that kind of disparity in something where it gets rarer and rarer. And so overall, students who score overall 1100 total, probably in the realm of 550 on one and 550 on the other, okay, in general. Okay, but of course, there's different exceptions. Yes?
So if we set d equals to 1, that's like reduce it to one dimension. And in that case, since we are creating linear combinations, how is it different from using linear regression?
It's yeah, if you reduce it just down to 1, it's kind of like linear regression, except the motive behind linear regression. So the motive behind linear regression is to minimize the squared residuals, and here the motive is to maximize the variation. Okay, and so conceptually it's similar. You're finding a linear combination of these things. You're basically taking each of the variables and multiplying it by some weight and adding them together, which is very similar to linear regression. Okay, but the coefficients that we settle on for linear regression is found by minimizing the squared residuals, and here we are maximizing the variation captured. Okay, which
is it going to be like consistent for the coefficient got from the linear regression and the weight vector?
The coefficients from linear regression will be different from the weights that we find here. Okay, if I said we want to minimize the squared residuals, we would get the same. Okay, but the goal of maximizing the resulting variation is different from the goal of minimizing the residuals. Okay, it's a subtle difference, but it is different. So maximizing the variation, and again, this is kind of the idea that when you look at the projection, you want it in such a way that that the resulting projection has like maximum variation, right? This one kind of minimizes the variation, right? Everything is just kind of piled on top of each other, so it's hard to see what it is, okay? But if you kind of spread it out, you get a better idea of the variation that exists. I'm debating how much I want to get into this versus like playing around with it. Okay. All right, I'll do this part kind of quickly, okay? So we'll just jump through some math here, okay? So to kind of simplify our life, all right, what we'll do is we're going to center the original data, okay? And that just means subtracting the mean from the column. So if you got 60 variables in your original Y data set, for each column, you will find the mean of that column, subtract that value from the mean of that, subtract that mean of the column from each value in that column, so that the average of the column will be 0. Okay, so you do that, and that's just centering it. You can scale it, you get something different. Okay, you don't have to scale it, but we're going to just say the column means are all 0. Okay, so that's what this is. Okay, so we're going to take the column means will all be 0. Okay, and here we're going to find the first principal components. So we're going to find the first vector of weights, the first vector of 60 weight values, so that the resulting projection, when I multiply W times Y, we will have maximum variance. Okay, and so when we multiply W times Y, we're going to get this, and the variance of X is defined as this. Okay, and so we want to maximize, we want to find the maximum value of this. We want to find the W's so that when we take this, it's as big as this could possibly be. Yeah?
I like you didn't say it. Why are we trying to maximize variance?
We are trying to maximize variance because variance can be like a proxy for the structure that exists in the data, right? So when I project the data from 3D down to 2D, okay, if I project it in such a way that the the resulting projection, the data all look very similar to each other, okay, then we've minimized the variance, right? So if I do such a way, like here's a stupid example. If all of my weights are 0, okay, I could take this 60-dimensional data set and I'm going to just multiply everything by 0, and so when I multiply my weights times the original data, the resulting projection, every value in my data set is 0. And now I have no variance in the resulting data, okay? I've basically lost, I've thrown away all the information that existed in the original data, okay? And if I do something else where the original data is projected in such a way that all the data points look similar to each other, we've lost a lot of information. What we want is that the projection, so that the resulting projection, the values in there look as different from each other as possible. And that means maximizing the variation. Okay, as far as a single value can go, variance captures how different the values are from each other, and we want to maximize that. We want to maximize how different the resulting values are from each other. And this is what we have, okay? So we want to figure out the weights W so that when we project it this way and calculate the variance, this is as big as possible, okay? All right, and so how do we do that, okay? Well, thankfully for us, okay, if we said we centered the data, okay, and if we centered the data, then the average, x bar, is also going to be 0, okay? So if y bar is 0, if I multiply that times some arbitrary set of weights, the result will also have a mean of 0, okay? Is that all right? Okay, and then so here's my variance, and this just simplifies this stuff, so I don't have to worry about this x minus x bar squared. It just becomes xn squared, xn minus 0, and so I want to maximize this, all right? So I want to maximize this, and x sub n is equal to the weights W multiplied by our original data y. And we want to find the W's that are going to maximize this quantity. Okay, so how do we do this, right? So basically, well, one thing, if we just wanted to maximize this, we could just set everything in W to be like infinity, okay? And the result would be huge, okay? But that's like cheating. So we give ourselves a constraint. We're going to say, all right, the norm of W, like the sum of the W's squared, have to be 1, okay? So we'll do that, right? So we're going to give ourselves a constraint, and but anyway, let's just multiply all of this out, okay? And so we get this W transpose Y and transpose W, which is a 1 by 1 value, and then and it's inside a sum, and the W's are constant, so that we can actually do this, okay? And this result, if I plug in that our y bar is 0, we can say is y minus y bar transpose, okay? And this is equal to the covariance matrix of y. Is that all right? So here I basically said the variance of our x is equal to our W times the covariance times the W. Covariance matrix of y multiplied by our weights W, okay? And so we want to maximize this, and again, a cheater way is just to set W's to be infinity, okay? But again, that's cheating, so we're not going to do that, okay? So if you can review this, but we're basically going to the covariance thing. All right, and so what we're going to do is we're going to give ourselves a constraint that W transpose W is equal to 1, okay? And so how do we do constrained optimization? Do we remember? Lagrange multipliers? Okay, yes, of course, right? Yeah, okay, so we're going to do a Lagrange multiplier, right? So we want to maximize this, but we include this constraint, the Lagrange multiplier, that W transpose W is equal to 1. So we have W transpose W minus 1 times lambda. Okay, we throw that in there. And then, we take the derivative of this, and then we get 2 times the covariance times W minus 2 lambda W is equal to 0, which reduces to covariance matrix of W is equal, oh, I gave you the answer away. covariance matrix of W is equal to lambda times the vector W. So I've got matrix times a vector is equal to a scalar times a vector. And from linear algebra, what does that mean? That the way this works is that W is going to be an eigenvector of the matrix C, the covariance matrix. So if we take the covariance matrix, like if you have a matrix times a vector, and that's equivalent to having a scalar times a vector, then that vector is an eigenvector of the matrix. Okay? We're okay with eigenvectors? Okay, so yeah. Multiplying by a matrix generally applies some kind of transformation to a vector, but sometimes the vector that gets transformed doesn't change direction, but just ends up being just scaled by something, all right? And if that's the case, then that vector is said to be an eigenvector of the matrix. Okay, so anyway, this shows that if we want to maximize the variance of the projection, the vector of weights that we're going to use should be an eigenvector of the matrix C. Right? And that's what principal components analysis will result in. Okay, is that we take the covariance matrix of our 60 variables. Okay, so if we got 60 variables, what is our covariance matrix going to be? 60 by 60. Okay, we got 60 by 60. And how many eigenvectors do I have if I've got a 60 by 60 square matrix?
60?
I'm going to have 60. I'm going to have, yeah, up to 60. But yeah, let's just say we're going to have 60, assuming no collinearity. We're going to have 60 resulting eigenvectors, okay? And what's going to happen is I can just pick the first eigenvector to get our first principal component. And if I want to just reduce it down to 3 dimensions, I can just take the first 3 eigenvectors, okay? And if there was a lot of collinearity in our 60 by 60 matrix, then some of those eigenvectors might all be zeros, okay? Or just might not exist, type of thing, okay? Yeah?
Are we going to have a break so I can get like
we can have a break after class, okay? I'm gonna keep going straight through, all right?
Well, I was kind of going to ask what you're talking about the past 5 minutes. I have been paying attention, but not enough to grasp it. But
Okay. You can ask your question, and I'll...
Yeah, why do we censor it, and what are all of these like big mathematical equations trying to say?
So we centered it to make our math easier, okay? By centering it, the mean is 0, okay? Because covariance is technically x minus the mean squared.
Doesn't center it just mean find the mean?
So centering means we've subtracted off the mean from everything, so that the mean of the column is going to be 0. Yeah. And all right, here's another kind of a visual explanation of principal components analysis. Okay, so here we have data in 2 dimensions. Here we got an x and a y, and the data look like this. Okay, and so technically the values exist in 2 dimensions, but really if I project them onto just 1 dimension, which is given by this red line here, okay, the values will look like this. And if I just throw away, okay, so if I project them down onto this kind of horizontal, or not horizontal, this diagonal line here, and I threw away the other dimension, I wouldn't be losing a ton of information, okay? The information that I would lose is the fact that this one is a little bit higher, you know, in this second principal component is a little bit higher, and this one's a little bit lower than average. But overall, they just kind of line up, right? And it's kind of, basically it's saying, you know, as x gets bigger, y also gets bigger. Is it always in a linear fashion where, you know, can we predict y exactly? No, there's a little bit of a scatter, right? And so here are the values in x, and here are the values in y. But here, because there's such high correlation between x and y, I can just project all the x values onto one principal component, and you can see the scale changes. Okay, here it goes from 0 to 10, and now it goes from negative something to positive something. Okay, and all the values in this principal component, this would capture the maximum variation. Okay, and then in the other principal component, all the values end up being very, very similar to each other, and so we have very little variation here. Okay, now of course, if I go from 2 dimensions here to 2 principal components, I haven't really reduced the number of dimensions, and so I'm still capturing all of the information. All the information that exists here also exists here. Okay, but the idea is that if I threw away the second principal component, what would I be losing? I wouldn't be losing very much information. There's not a whole lot of variation that was captured in the second principal component. Okay, and this is an interactive thing, which is kind of neat. And so I can actually drag these observations like this. Okay, and so here we can see what would happen if I drag these observations like this. Okay, now I would lose more information. Okay, so the first principal component, to maximize the variation, has this, but we would lose the fact that these 3 observations are they end up being quite similar to each other in as far as the first principal component direction goes, but they are for the second principal component, they exhibit some dissimilarity. So this one might be the so if this is like SAT scores or something, this might be the student that scored 800 on the verbal and 300 on the math, and this might be the student that scored 800 on the math and 300 on the verbal or something like that. Okay, but again, you know, we're not losing as much information that way. Yeah.
It's in 2 dimensions again.
It's always been in 2 dimensions. Okay, so here we're going from 2 dimensions x, y, and we're going into 2 dimensions PC1 and PC2. The idea is, if I throw away PC2, what would I be losing? Okay, and we would lose a little bit of information. Anytime you go from higher dimensions to lower dimensions, you lose information. The question is this an acceptable amount of information loss? Okay, and for the sake of convenience, a lot of times, yes. Okay, a lot of times, for the sake of convenience, we're willing to throw away information about a student's academic life just so we have a single GPA number to make quick comparisons from student to student. Okay, we're willing to throw away a lot of complex notions about intelligence to get two numbers that are easy to compare with. Okay, yeah.
So like, say hypothetically, say everyone has grade inflation now. So like our GPA variation now, instead of spanning the whole scale, like from 2, it starts spanning from 3.5 to 4.
Yeah. So right. Then there's an argument for scaling and things like that, and it's difficult, and we recognize the problems of using a single number to summarize things. Right. Anytime you use a single number to summarize something complicated, you get all sorts of weird things of people trying to game the system and people trying and just it being an inaccurate measure, right? I don't know, like when I went to high school, like the AP classes, you could get 5 points, and if you took a regular class, you would get a 4 point, right? And then you got weird things where it's like, oh no, if I take PE, the max is I'm going to only get 4 points, so I don't want to like take a sport or PE because that's going to factor into my GPA, and I would have gotten a 5.0 this quarter, but I want weird stuff like that, right? Or like, oh, you have to take driver's ed and health or something, but I don't know, is that class even part of your high school curriculum? Okay, all right, well, something, right? There might be some class and you're like, no, it's better for me to take driver's ed at the local driving school than taking it at my high school, so it doesn't factor into my GPA where it's going to count only 4 points versus 5 points. Like, this is ridiculous, right? But this is the side effect of saying, oh, the GPA is what colleges are only going to look at your GPA, and if it's over this number, you're in, and if it's under that number, you're out, type of stuff, right? There's problems with dimension reduction, okay? Do we still do it? Yes, because it's useful. It's easy. It's easy to compare one number at a time than to say, let me sit down with a student and interview them for 45 minutes to find out their life story and then decide if they, it's too hard, right? It's just like your grade in this class, right? You get a single number, and as if this were to magically represent your knowledge and understanding of the class. It's imperfect, right? I came up with some arbitrary thing that says your homework 1 is going to count 6%. That's a linear combination of the different things you've done in this class, right? Homework get weighted at 6%, and the midterm get weighted at 30, and the final gets weighted at 30, and random stuff. It's a linear combination of the things you've done in the class, reflecting maybe how important I feel this thing is as a measure of your academic performance, okay? Imperfect measure, yeah. We lose information. Okay. So here is a 3-dimensional example. We're going to project the 3 dimensions down to 2 dimensions, maybe even 1 dimension, okay? And we want to do it in such a way that the resulting projection has as much variance as possible in the first direction and less in the other ways, okay? And so this is what the data look like in 3D, okay? And I can change the way the projection works. Oops. Is this not how it works? Okay. So I can try to figure out, like, how should I project this, okay? Red is the maximum thing, and so I want to maximize the variation that appears, okay? So probably something like this. This is going to maximize the variation that I see here. Okay, now when I click this, it's going to calculate it for me. So when I click Show PCA, this is how we've maximized the variation here, okay? And so an interesting thing is that when you look at the projected data, it seems clear that there's actually like 3 clusters of data, okay? Like 3 balls of points, okay? And in the original X and Y and Z, the 3 clusters are not apparent, okay? We can kind of see like 2 clusters here and 2 clusters here, and maybe a hint of a 3rd cluster here, I don't know. But when you do the principal component projection, you find the 3 clusters defined a lot more clearly. Yeah?
Okay, so now we get to the group that lays the golden egg, in case where the projection is telling us something that's not in the dimension. So now the question does become how. I think you've been explaining a lot, but I haven't really got it. Yeah,
so again, by maximizing the variation that we see in the projected data, it will often uncover.
What does that mean, maximize the projection?
So all we've done is we've taken our y's, we multiplied by them by weights, and we added them together, okay? And we have different different weights for each dimension in y. So currently, our original data, our data exists in 3 dimensions, and we're saying we're gonna multiply x by some value, y by some value, and z by some value. Our 3-dimensional data, each of them get weighted by something. We add them together, and we get PC1. Okay, and so this variable, the result PC1, will have a mean, will have a variance.
So are you saying that maximizing the weights?
Yeah, we're trying to figure out what weights to use, which are best, so that the result of this will have the biggest variation possible. Okay, because it's possible I could just say, well, let's just multiply everything by 0 and add them together. Then every single value will just land up on 0. Okay, that will have minimum variance. That's how we get 0 variance in the resulting data.
The point is that the PC1 y is actually x, y, z sort of compressed together, and x is sort of x, y, z compressed together.
Yes, yes. So when we do our principal components, is that this is, yeah, some weighting of x, y, z, or in the other notation, y1, y2, y3, up through y60, okay, compressed in such a way, or like multiplied in such a way and added together. Yeah, we take all these numbers and we just boil them down to 1, okay? And we've done it in such a way where the weights have been chosen so that the result will have a great amount of variation. Yeah?
Even on this, like, there is sort of like a downwards arc if you were to just draw like a centering line on that graph, but it's still going up every time. But here it's just like up, it's like up and then down again.
Yes, so here's the thing is, anytime you go from higher dimension to lower dimension, you are giving up information.
I understand.
Yeah, and so yes, there is an arc here that exists in the second principal component, okay, that we lose. Well, technically, if I keep PC1 and PC2, that arc is preserved, okay? We've projected from 3D down into 2D, and we've projected that. What we've lost, okay, is technically the third dimension, which looks like this, okay? We've lost the fact that there's a point over on this side and there's a point over on this side, okay? We've lost some information, but we might consider that an acceptable amount of loss of information for the simplicity of going from higher dimensions to lower dimensions. Yeah. All right. So here's another example. We're looking at diets of. Yeah.
Question. From the the axis, you can see that there's about 3 clusters, right? I'm wondering whether the PCA can give like the 4 or 5 clusters. Is that possible?
Do 4 or 5 clusters exist in the original data? So the goal of PCA is to preserve the most amount of variation, as much variation as it can in the original data using fewer dimensions. That's kind of the goal, okay? So the original data has all the variation that exists, okay, that exists in the data. And we're saying, like, can I have only a few variables that still captures the kind of the variation that exists in the original data? And so in the original data, I think 3 clusters exist, and so the PCA is going to kind of reveal that as well. But that's what we have. Okay, here is the United Kingdom of Great Britain and Northern Ireland, right? And the United Kingdom, it's called the United Kingdom because if you studied your medieval history, there were three different nations on Great Britain, and then there's the island of Ireland, and there was religion and people fighting and Braveheart, and so you have Scotland and Wales and England on Great Britain, and then you have Ireland, and they didn't agree, and so there's Northern Ireland, and then the rest of the Republic of Ireland, okay, and Brexit is basically anyway. All right, how do we handle Ireland and stuff? Anyway, we asked them, like, what food do you eat, right? How much alcohol do you drink? How much cereal do you eat? How much fish and fresh fruit and potatoes do you eat? And we asked, there's 17 different things, and we said, how much of this do you eat, right? Okay. And so when we do print, so I don't know, do any of these countries stand out as significantly different from the others? Okay, with 17 dimensions, it's hard to see, okay? Our eyes are not good at comparing and keeping track. Our brains aren't good at keeping track of 17 different categories all at the same time and saying, oh, that's strange, that one's different, okay? Okay, so when we do PCA, look what happens. We get Wales, England, and Scotland together, and Northern Ireland is super different. What do you think makes Northern Ireland super different? It's exactly what you think it's going to be, right? You look at Northern Ireland and you look at potato consumption, all right? And England is 720, Scotland 566, Wales 874, and Northern Ireland 1033, right? And you look at fresh potatoes versus fresh fruit, okay? England more fruit than potatoes. Scotland, more fruit than potatoes. Wales, more fruit than potatoes. Ireland, more potatoes than fruit, right? You look at other things like alcoholic drinks, okay? England, Scotland, Wales, more alcohol consumption. Northern Ireland, less so, and things like that, okay? And so anyway, we have all of this, and that's what it basically points out. And so so anyway, it gets plotted as such in the first principal component. Second principal component says, oh, you know what, Wales and Scotland, those are quite different in some other aspect, and I'm not exactly sure what that is. We would have to look at kind of the weights that get selected there, okay? All right, is that all right? All right, so here's just kind of a fun example. I think it's fun. Oh, here, let's do the heptathlon first, okay? So I gave this example, I mentioned this example earlier. So now we're gonna run out of time. We'll skip the heptathlon. Okay, so basically the results of the heptathlon is heptathlon being 7 different events like hurdles and, I don't know, 800-meter run and javelin and shot put and high jump and long jump and 200-meter run. I don't know, something. Okay, don't quote me on that. And so so if you do principal components analysis on the heptathlon data, you will find that it matches, that the results of the heptathlon PCA matches kind of, in the Olympics, they have a way to combine the results of the 7 different events into a single score, and it's weird, okay? Let me look up Olympic heptathlon. Okay, women's heptathlon, 100-meter hurdles, high jump, shot put, 200 meters, long jump, javelin, 800 meters. Okay, and then and basically you take these coefficients and you take your time and whatever, and you factor it in here, and you get your points, and then you add them up. Okay, and this is how you get stuff, and this is you know, your best performing stuff. Okay. So anyway, what we would find is that if we performed PCA on Olympic results, the results correlate very, very highly, like 99% correlation between the Olympic scoring system. Okay, so the Olympic scoring system has found a way to distinguish gold medal performers from the rest based on some combination of the seven results, and results of PCA do the same. Okay, here is here's a fun, I don't know, maybe fun, I think it's fun, application of PCA, maybe impractical. Okay, all right, so I'm going to just load up an image here. It's weird. Okay, so here's a picture of Audrey Hepburn from the movie Breakfast at Tiffany's, okay? And this image is 634 pixels wide by 791 pixels long, okay? And if we think about what an image is, it's really just a vector, or a matrix of 634 by 791 values, okay? So we can just think of this as a matrix where each value in our matrix represents how bright or dark a pixel should be, okay? And so we're going to say, you know, bright pixels are like 255, dark pixels are 1, or 0, and anything in between is going to be some shade of gray, okay? And so if we think of our matrix, we can say we have 791 observations, okay? 791 observations, 791 rows. And each of those rows has 634 dimensions in it, okay? So in order to create this image, I need to have a very large matrix, okay, of 791 by 634, which is, I guess, 1,500,000 values, okay? And in uncompressed form, just keeping all of those kind of floating point values, is 11.5 megabytes of space, okay? Just for a black and white image. Now, we have image compression these days, and so it doesn't actually take up that, but we could imagine a principal component-based image compression technology, okay? Where instead of preserving all 634 dimensions in the original data set, I could choose to preserve maybe 100 of the 634, okay, or 50 of the 634, okay? And if I'm still able to capture the variation that exists in the original data such that the image looks the same, then we're good, okay? All right, so how are we going to do this, right? So principal components analysis says to find the weights that will maximize the resulting variation, what we're going to do is we're going to center the matrix, find the covariance of the centered matrix, and we're going to find the eigenvectors of that covariance matrix. Okay, and that will give us the weights. I know we just did it a couple minutes ago, but I'm telling you, that's what we're going to do. So first I'm going to center this matrix. So again, think of this as a giant matrix of 791 rows, 634 columns. So I'm going to take the column mean and subtract the column mean from every value in here. Okay, so what will that look like when I do that to our picture of Audrey Hepburn here? Okay, so here I take the column means and I'm going to subtract it all, and I ask, are they all equal to each other? And it tells me true. Okay, and we can plot the centered image. Okay, what will the plot of the centered image look like? What do you think? Will it look like this? Okay, so let's think about what it is. Let's look at this, the very leftmost value. Okay, so each column, right, represents kind of a column of pixels. Okay, so if I look at this column kind of going down her arm, where she's wearing this black glove, okay, what is the average of this column going to be? Okay, it's going to be quite low because black is a small number, right? Okay, and look at this column where there's a bunch of bright white pixels. It's going to be high, right? So if I take the average of this column, it's going to be high, and if I take the average of this column, it's going to be quite low. And if I subtract that and do this, what's going to happen is that it's going to basically effectively darken by subtracting off a value. It's going to darken the column of pixels where there's this bright white, and it's going to brighten the column where it's black, okay? And such that the overall color of the image, if I average this, everything will have an average of 0, which I guess in this case will be kind of scaled to gray, okay? And so we see these kind of vertical streaks. I don't know if you guys can see this. We have vertical streaks where parts of the image where there's a lot of white, that area generally gets darkened, and parts of the image where there's a lot of black generally gets brightened, okay? And so we get these we get this streaky image, okay? And it's hard to picture this in our brain, or not picture, but know this exactly just off the hands, but the average of each column is now 0, okay, which is, I guess, some generic gray, okay. So anyway, I'm going to find the covariance of this thing, okay. And so the covariance matrix, if I ask what's the dimensions of this covariance matrix, it's 634 by 634, and I'm going to find the eigenvectors of this, okay? And if I ask what are the results of the eigenvectors, I get eigenvalues. I got 634 eigenvalues and 634 eigenvectors, okay? All right, and so what I'm going to do is I'm going to say, let's just keep the first 50 out of 634. Okay, I'm going to just keep the first 50. And so I'm going to just here take the eigenvectors and preserve only the first 50. Okay, and so if I ask what are the dimensions of this, it's 634 by 50. Okay, and I can, so these are the weights, right? So I've got 50 weight vectors. Each of those weight vectors have 634 values in them. That's what we have here. And if I multiply this times my original data, which is 791 by 634, the result will be what? The result will be a matrix of 791 rows, but now only 50 columns. Is that okay? What does it look like? Yeah. What does this look like? It is, it's not going to look like anything meaningful. Okay. I'll plot it. Okay. So this is odd projected. Okay. So what we've done is we have 791 rows. In our original data, 634 columns. I found the eigenvectors, okay, and I kept only the first 50 of them, which is 634 by 50. And I've multiplied all 791 rows. So the first row was 634 things long, and I multiplied it by the 634 by 50 thing, and so this first thing turned into a vector of now only 50 values. And I did that for all 791, so now the result is a matrix that's 791 by 50. Is that all right? All right. What will this look like if I project it? It will look like gibberish, okay? All right. This is what it is, okay? It just looks like a gray column, okay? What happened to poor Audrey Hepburn? But it looks just like gray, all right? But contained in here, okay, is kind of almost all the information that we need, okay, to reconstruct the image. All right, so to reconstruct the image, I just need the weights, my 634 by 50 weights, and my projected data, which is now 791 by 50. Okay, so I've got the projected data, 791 by 50, and I've got my weights, which is 634 by 50. I'm going to transpose my weights to be 50 by 634, and I'm going to multiply this matrix 791 by 50 times the matrix of weights transposed 50 by 634, and that will reproduce something with the original dimensions of the original data, 791 by 634. Is that all right? So here I'm going to reconstruct the image by taking our projected data. This is 791 by 50, and the transpose of the weights. Here it's 634 by 50. It transposes it to 50 by 634. So this is 791 by 50 times 50 by 634, and that's going to result in a 791 by 634 image. Okay. And what I will do now is I will add back the means that I subtracted. Okay, because right now, because we subtracted the means, so it was a streaky image, we're going to add those means back in. Okay, And so let's take a look at what this looks like. It looks a lot like the original image. This image, I don't know if you guys can see a little bit of blotchiness here, okay? A little bit of artifacts, okay? This image was reconstructed from two matrices. One was 791 by 50, and the other was 50 by 634 after I transposed it, okay? So I have two matrices, 791 by 50 and 50 by 634, and by multiplying those two together, I've reconstructed this image. Okay, how does this compare to the original image? Okay, so this is the original image. I don't know if this projector you can tell the difference. Original and the reconstructed. Okay. Oh, so there's. It's getting mad at me. Huh? Okay. Reconstructed and original. Okay, so if you look especially at the ceiling where the original image is this nice even black color, and this is very almost white, and her gloves are very dark black, okay? On the reconstructed image, you know, you get a little bit of blotchiness in those areas, okay? And this is reconstructed based on a much smaller thing, okay? At a practical level, we don't do this for the computers because it's very computationally expensive, okay? To find the eigenvectors, it takes a lot of computing power, and then to do a big matrix multiplication, it also takes a high amount of computing power. But it's theoretically possible, okay? We just did it, all right? We just did it, yeah.
So, is it possible to like have a pixelated image and then do that like reverse and then get a depixelated?
No, it's not. You can't do image enhancement based on this, right? We've thrown away the extra information, okay? When we went from 791 by 634, which has, I don't know, a lot, okay? We went from 791 by 634 to 791 by 50. So we've thrown away, we've reduced the number of columns by like, 1/12, okay? Now we have to keep the other matrix of weights, okay, which is 634 by 50, which is, about 1/12. So maybe, we've reduced the number of raw values to keep to about 1/6 the thing, okay? All right, so here I said, well, what would happen if I just keep one? So here I kept 50 principal components, but what if I only kept one or 10, 2 or 3 or something like that, okay? So here I did a bunch of these things. I'm not going to run the loop right now, okay? Because I've already done it. And I'll just show you the results. Okay, so if you only keep one principal component, okay, the image is not recognizable. Okay, so this is, so here we've kept just one principal component out of 634, okay? And we get something that looks nothing like this, right? What's close is that this is kind of light, white, and we got that, and we get some lightness here, okay? Here's with 2, and we get a little bit more definition in kind of this bright white area, and this area that's a little bit brighter, and this area that's brighter. Maybe we get a little bit of darkness here, kind of her arms here, and maybe a bright white area where her face kind of is, okay? 2 principal components, going from 634 down to 2, okay? Here it is with 3. And 4 principal components kept, okay? And we're starting to see a little bit more of kind of the definition of some of these features that exist here, right? There's 5. And then when we go to 6 principal components, suddenly we see something that looks kind of like eyes, right? We're like, oh my goodness, all right? Maybe that's a person in there, right? It's kind of, I don't know if you remember, like, there's this terrible movie called like, I don't know, Life on Mars or something, and people, old images of Mars, they thought there was a face there, and it turned out to just be a funny shaped rock. But it was kind of like this. They saw a rock that looked like this, and they're like, oh my gosh, face on Mars. People were there and stuff. Okay. All right. So anyway, 7 principal components. And here at 10 principal components, I would say if you saw a thumbnail of this, you'd be able to guess that this was this image. Maybe? I don't know. Because, well, is this not an internationally recognizable image of, like, you guys never, okay. Like, all right. It's not even, it's like a historically significant movie. You guys are breaking my heart here. All right.
Just Google her name. She died before I was born.
Huh?
I just Google her name. She died before I was born.
Of course. So did whatever, Cary Grant and Frank Sinatra. All of these people are dead, right? You guys know Frank Sinatra. Kind of. He's dead? Yeah, he's dead. Wait. Okay. Well, I don't know. Important for American cinema, okay? All right. Okay, so anyway, here I am at 18 principal components, and we're keeping more and more and more. So I started jumping 25, 30, 35, 40, 50 principal components. And as I go, you see, you know, a little bit more. It's like turning up the contrast on the image, okay? Which is effectively, what is turning up the contrast? It's increasing the variation in the brightness of pixels, okay? High contrast means the white is very distinctly different from the black, okay? That's what high contrast means, right? And then low contrast means the white and the black are not that different from each other. And so turning up the contrast is just increasing variation, all right? If you got increasing the brightness on your monitor, that's just shifting the mean up, okay? And increasing the contrast is increasing the variation that you see, okay? And that's basically what we're doing. We're keeping more principal components, so we're able to keep more variation in the original data, which means we're going to have more contrast in our resulting image. So that's why it looks like we're not just brightening the whites, we're brightening the whites and darkening the blacks, okay? So here, as I go up, the white areas get brighter, and then the black areas get darker, okay, as I increase the number of principal components, okay? And that's what increasing the contrast is, okay? So here at 210, I mean at 180 versus 210, it's like I don't even see a difference in the image here. I'm looking on my screen. Huh?
In the eyes.
I guess in the eyes, maybe, okay? And so, you know, and at the point where you're keeping 300 principal components, you're not reducing the amount of data that you have to store, because you have to preserve the projected data plus the weight matrix, right? So at this point, I'm preserving a matrix that's 791 by 300 and 300 by 634. That's a lot of data to keep, right? So obviously, if I kept all of them, I'm actually increasing the amount of data I have to store. But anyway, this is at 500 principal components. Now I would say it's difficult to distinguish between this and this, even though technically we've lost some information. Yeah, Yoni.
So PCA with like 30 variables, what actually is? What are the variables?
No, the original data has 634 variables.
Each variable takes.
Each variable is a column of pixels. Okay, so we've got a matrix that's 791 by 634, and each variable in the original image is a column of pixels. Yeah. And we're trying to maximize preserving. Yeah, if we keep all the columns, we haven't reduced the number of dimensions. Okay. The question is, can I preserve the variation, the structure of this data? Can I preserve the structure of this data without having to keep all 634 columns? Okay. And the answer is yeah. If I keep, say, 30 30 columns out of the 634, I have maintained quite a bit of the original structure in the data. Okay. Now, of course, this is with an image, like our eyes are good at seeing stuff. Okay. But in real life, you might have a very complicated data set with like hundreds of variables. Okay. And you don't know which of these variables are important. Okay? You got your housing data set with 60 variables. Are all 60 variables important? Okay, maybe, but probably you can reduce it to 5 variables or 10 variables or 3 variables and preserve a lot of the structure, right? And you might just reduce all of those house size variables, how many bedrooms and bathrooms and square footage and size of the basement and the lot size. That all might be reduced to just one variable that says, that goes from, that's like big house versus little house, right? And yeah, that might mean when you reduce all of that information down to just one number, like is it a big house or a little house, you might miss out on some stuff that says, oh, you know, this is a big house with very few bedrooms, or this is a small house with a lot of bedrooms. Like you might miss out on stuff like that. But overall, probably in the general data set, those kinds of exceptions are fairly infrequent, and we have simplified our life by just having a couple variables to keep track of, right? For example, when you go, like if you go on Airbnb, okay, and you're looking for a place to stay, so let's say we want to go to Las Vegas, all right? We want to go tomorrow, all right? By yourself, okay.
Just before the final.
Yeah, why not, right? Okay, so you go where to stay, right? What have they done? They have reduced the variables, okay, that you see to what? They reduced it to 2 things, price and stars, okay? And this, by reducing the amount of variation that they have on this results page, you are able, oh, I'm sorry, there's a couple other things, right? Number of beds in the thing, okay? By reducing it to this, you are able to make decisions quickly in terms of like, do I want to check this place out, right? So they've got a picture, I don't know how, that's something else, right? But they've got a price per night, star rating, and the number of beds. And this is enough, okay, for you to kind of just say like, oh, all right, I'm not going to click there, I'm poor, right? So we're going to click here, okay? All right, Central, the great attraction. Oh yeah, let's look at this. 48 a night, 4.95, that's great. Okay, 2 beds, private room, all right, okay. So I guess private room is another variable that they've kept, right? But then when you click it, then there's a whole bunch more other variables that they keep track of, right? And I don't know if you've ever tried to download the Airbnb data set, but every single one of these things is like a dummy variable, is a variable in your data set, and it's going to say washer 1 or 0, and it's going to say air conditioning 1 or 0, and heating, you know, it's going to say this place has heating and this place has air conditioning, right? And it's, you're like, I guess the Airbnb website isn't smart enough or isn't designed to this where, you know, you're going to just assume all places have air conditioning, but some places don't, right? And if you're going to go to Las Vegas and it doesn't have air conditioning, that's a serious issue, right? But I guess, so that's kind of like your user beware. And you're hoping that this 4.95 contains the information, right? You might see another place, 2 bedrooms, $48 per night, and maybe it's only got 3 stars. And you're like, why does it only got 3 stars? And you click and you're like, oh, they don't have air conditioning, that's why. And so this thing we're assuming contains, there's something about this that contains a lot of information. Yeah.
Would you just assume like the pictures also represent information?
Yeah, yes. The pictures were okay. We don't have a way to summarize pictures yet. Okay, we have neural networks, and this is a whole topic of research over here. that yes, the pictures contain informations. You got old adages, a picture is worth 1,000 words and things like that. And it's true, a picture contains a lot of information, but right now, our computers are not smart enough to turn the picture into an assessment, okay? So just assuming, you know, and if you, you know, click this and, you know, there's all sorts of stuff, amenities, okay? And yes, it comes with shampoo and hair dryer and hangers and all of this stuff, right? So you know, basically, if you go to Amazon, same type of thing. So I don't. Yeah. Okay, let's say we wanted to search for
Chargers.
okay, phone charger. All right, let's go iPhone charger. Okay, so we're gonna go iPhone charger, right? And they have reduced the information that you can see basically just to the star rating and the price. Okay, and it's only until you like, and then there's the title, which is now a mess. Okay, everything on Amazon, it's like they've crammed everything into the title of the product, and so you get Kozopo phone charger, durable USB cable, 6-foot 2-pack, fast charging data sync transfer cord with 2-port plug, travel wall charger compatible with phone X87 plus 6S, 6SE, 5S, 5C. Okay, and it's like, I hate you, but okay. So this is what we have, and then there's more information. You know, probably the bits of stuff that are maybe a little bit more organized are, I don't know. I don't know. There's more variables here about input and output, but it's a lot messier. Okay, so anyway, dimension reduction is an important thing. Okay, and we don't even realize it, and it's only when you go to a search website, and I can't think of an example right now, but pretty much any place that's customer facing, when you do a search result and they show results, they have reduced all of the information down to what they think are just like the 1 or 2 most important aspects of that product, right? So on Airbnb, they reduced the search results to just like the star rating, the price of the place, and all of that. And if you want more information, you can get it. And it's frustrating if you ever interact with a search engine where it gives you too much detail, right? You get, like, you search for something and it just gives you like way too much information. And most websites don't even have that because they have these user experience people that say don't give them too much information, right? But that's what we like as people. We like summary information, okay? Because our brains have a hard time keeping track of all of this. And that's going to be an important thing for you to learn as well. If you go to the workplace, all right, and you have a boss or your boss has a boss and you need to submit a report, that person probably has to look at 50 different reports a week or whatever, and they don't want all the detail. They just want the summary points, right? And you have to learn how to summarize all of the relevant bits of information in such a way that that captures the important aspects of the data. And so anyway, so principal components analysis allows us to reduce the number of dimensions that we have by trying to preserve the variation that exists in the original data. And things that you can do, I mean, you could do PCA for PCA's sake, but other things you can do is then you can perform regression on the resulting principal components. So probably when you did your housing data set, you just plugged in all 60 variables in the housing data set, okay, and you did some kind of analysis. But you could have also done some kind of principal components analysis and maybe come up with these 3 different scores, right? The size of the, I don't know what principal components of analysis would have resulted, but you could have come up with these other variables, and then you would probably had a much simpler regression model to explain. And you just say, as far as price of the house comes, like the neighborhood desirability factors in this much, the size of the house factors in this much, and the amenities of the house factors in this much. And you can say, but then you'd have to explain that neighborhood desirability goes from 1 to 10, and it consists of these other things. And a 1 basically means high crime and poor school ratings and all sorts of other problems. Okay, and 10 means surrounded by mansions, super nice area, whatever. They, and your typical neighborhood probably scores a 7, and stuff like that, or something like that. Okay, and then you'd have to say, as far as size of the house goes, a 1 means it's like a studio, or your typical 3 or 4 bedroom house will score like a 6 on the thing. I don't know, as far as this, and then a 10 will be the mansion that, I don't know, who has a really big house? I don't know. Somebody, right? Stuff like that, okay? And so the disadvantage of principal components analysis is that you have to explain what these principal components are, okay? Because if you just say PC1, nobody knows what that means, okay? But it might be easier to find some kind of regression analysis there as well.
I don't know what PC1 is once you run.
Yeah, so you don't know what it is, okay? It's just the computer says, or the eigenvectors say, this is the resulting principal component. Now what you have to do is you have to look at the weights that have been assigned to PC1, okay? And you'd look at the weights and you'd say, these variables score high positive weights, these variables score small weights, and things like that. The interpretability of the principal components is not as easy as I've made it out to be, okay? I've made it out like, oh, it's gonna find the housing things and done it this way. It's not, it's generally not like that. It's a lot requires a little bit more stuff, and there's probably a blend between pure PCA and then making your own variables, okay? So you might do PCA and it might say, do 0.9 of this variable, 1.2 of this variable, and 0.7 of this variable, and negative 0.3 of this variable, okay? And you might take that and say, you know what, let's just make our lives easier and just take 1 of this, 1 of this, 1 of this, and negative 1 of this, or something like that. And you might create your own custom variables based on the results of PCA, okay? Or you can go straight off of PCA as well. But there's stuff to that. Okay, anyway, it's a neat topic. Just kind of from a conceptual standpoint only will be covered on the final exam. Okay, we'll end there, and good luck as you study, and we'll see you guys on Wednesday.